Can cyclists cheat by drafting behind a motorbike during a race? If you've ever watched a cycling event, you probably have seen these motorbikes with camera crews on them riding around. And these motorbikes are often just ahead of cyclists and sometimes even just ahead of one cyclist. So the drag a cyclist feels is very high and a major limiter to the top speed you can reach. So if you were to sneak and draft behind a motorbike during a race, can you go faster or conserve energy so that you can ride harder later and shave off some time and even win? That is what we're looking at today. Do the motorbikes in these cycling races affect the outcome of the race through their aerodynamic effects? To find that answer out, we're looking at this paper here called, if I scroll up, Aerodynamic Benefits for a Cyclist by Drafting Behind a Motorcycle. And while this primary focus of this podcast is about how these motorbikes affect a cyclist's aerodynamics and a race's outcome, as you will see later on, the CFD is really terrible in this paper, and in my opinion, it has been massaged to make it look much better and make it look like there aren't as many errors in there as there really is. So that is my opinion, and I will go through that later in this podcast, why I think that, and you can make up your own mind as well about that. So anyway, you can find this paper in the link below, and let's get back to this regular podcast. So I don't cycle, and I did for a few months, but I didn't enjoy being punched in the boys 1,000 times every ride, so I stopped. But I do like the aerodynamics behind cycling because it is incredibly transient. That's because your legs cycle around, and as they cycle around, one knee goes from being high to being low, and then the other one goes from obviously being low to high. And that comes with a very dynamic response to the air, and hence the drag that you feel throughout this entire cycle. Then coupling that with well-known tactics of cyclists drafting behind each other, that then creates even more complex aerodynamics. And then now, throwing the motorbike, it's even more complex. And the thing is that these races are pretty much inundated with foreign objects. You have these motorbikes, but you also often have team cars that follow cyclists, and these cars are there to support the cyclists with various tools and equipment. But interestingly, the effects of a team car following a cyclist even reduces the cyclist's drag by 4%. So imagine having a 4% advantage. One interesting thing is that the motorbikes aren't allowed near the cyclist in the last 500 meters of a race though. So that is a strong indication that the board of governing these races might know the benefits of motorbikes on the cyclist aerodynamics. It could also be that the motorbikes pose a safety hazard, and because like if you were to cycle and try to overtake, you might hit the motorbike or cause some kind of injury. So that's why they limit it too. So anyway, to find out if and by how much a motorbike changes the drag of a cyclist, these researchers did some wind tunnel experiments and some CFD. And just quickly, if you want to learn OpenFOAM, which is a completely free and good CFD software, but hard to learn, check out our course in the link below. But back to this podcast. So their rider and motorbike wind tunnel geometries can be seen in figure 2. So let's scroll down to those. Here we go. And I can't find any mention or hint about the rider moving its legs during the wind tunnel experiments. I mean, it's not a real person, but if you had a moving ground, the wheels could have been rotated and that would allow the legs to rotate as normally. But in figure 3, we see the geometries installed in the wind tunnel, and it doesn't seem like there's any moving ground. The cyclist is just on a turntable. So that is a major limitation to this study. The cyclist is static. Nevertheless, it does still give us a good idea about the kind of drag effects we can expect. So the cyclist and motorbike setup was a quarter scale setup, and that resulted in just a 2% blockage ratio, which is really low. And with that blockage ratio, you usually don't need to put any wind tunnel correction factors into it. And the turbulence density was 0.3%, which is much lower than what you would expect in real life, considering that the cyclist would be in the regular environment. But because it is in the wake of the motorbike, the turbulence density doesn't directly affect the cyclist here. So the question is, does the turbulence density affect the motorbike aerodynamics, which then would then affect the cyclist in sequence? So the turbulence density does affect the motorbike a little bit, but because it is so bluff and the actual geometry of the motorbike setup changes all the time, depending on the people who are on it and the equipment and so on, I don't think that it makes too much of a difference here. So this is more a general investigation and not a specific setup for one particular geometry. So the results here, because of this turbulence density level, is still applicable from the point of view of just being general. One thing that is important to note is that the boundary layer in this wind tunnel is a little bit different to what you would expect. So they say that as the flow reaches the cyclist, the boundary layer is building up to about the cyclist's feet. So these researchers say that as such the case, a very small fraction of the cyclist setup is in the boundary layer, and hence they suggest that perhaps it doesn't really matter too much. But I think this still poses a bit of a problem. So to begin with, a cyclist won't necessarily see a boundary layer, only if there is a wind with a boundary layer developing over the ground and then impacting the cyclist. So we can conclude right there that with this particular setup, this matches if there is a headwind. But what if there was no wind? Is the boundary layer here still okay? From what I can see from the researchers saying, it seems like they're implying that these boundary layer effects are negligible, but I don't agree with that conclusion, and I'll give you a real life example to show you how connected a boundary layer is to the rest of the flow physics over an object. So many years ago, I went to one of my friend's offices to go to lunch, as we did all the time, and this time when I got there, he was deep in thought about why something was happening to the flow over an object he was researching. And he was investigating the aeroacoustics of cylinders at the time. And what he was finding was that depending on the roundedness of the top of the cylinder, the boundary layer height was different. So the strange thing is that the distance between the top of the cylinder and the boundary layer at the base of the cylinder was really far, relatively speaking. It was like 10 cylinder diameters away. So why was there such an effect? How could the top of this object affect the base so much and the boundary layer? Well, we thought about it and we were motivated by hunger, so we figured it out pretty quickly. And we found out that the flat end of the cylinder made the flow separate compared to the round top, which allowed the flow to stay almost completely attached. That difference in flow at the end of the cylinder created a different pressure, and hence those pressure differences pulled the boundary layer up by different amounts, hence making the boundary layer a different height. So that literally means that something going on at the other end of an object can affect the boundary layer still, which shows you just how connected the flow physics is over an entire object, and the importance of a boundary layer is well known in so many different fields. So that is why I'm not convinced that this relatively small boundary layer isn't negligible when it comes to the aerodynamics of this rider. Its presence could easily change how much the flow gets squashed. As such, I think the boundary layer will introduce probably a couple % error here. So anyway, one cool thing they did was they tested at different velocities, from 15 meters per second to 30 meters per second. And they noted that above 20 meters per second in this wind tunnel, the results were now Reynolds number independent, and they reported those in the results section, the Reynolds number independent part. Now, when I read that the maximum velocity tested at 30 meters per second, I was a little shocked because 30 meters per second is about 110 kilometers per hour. I thought that was really fast for a rider, so I looked up how fast they do go. And it turns out that the average velocity over a 200 kilometer race is about 45 to 50 kilometers per hour. But when you go down hills, they can get over 100 kilometers per hour, and someone even clocked it 130 a few years ago. So they can get to 30 meters per second, and the Reynolds number independent point here is at least 20 meters per second, which is around 70 kilometers per hour, which is far more normal. So they tested this rider at a number of distances behind the motorbike with the full scale values corresponding to only 12 centimeters up to 50 meters. So imagine traveling at 70 kilometers per hour, only 12 centimeters behind a motorbike. They say that from their uncertainty analysis, the drag coefficient had an accuracy of 0.8%. That is just the force. There are still other inaccuracies compared to reality, like the boundary layer. So if I were to ballpark the uncertainty of this experiment, it might be around 5% in total to what you'd find actually on the road. With that, let's move to the CFD setup. So they did the CFD setup on a full-scale model, and the CFD setup was identical to the wind tunnel setup except for the mounting equipment needed for the wind tunnel. So here you can see there's a few things on the ground which they don't necessarily have in the CFD. They don't need those things. And in figure 4, we can see their mesh. So one thing that I'm a little curious about is the mesh sizing between the motorbike and the cyclist. So you can clearly see that the motorbike is in a square refinement region. That's good. But the downstream region ends quite soon. That's bad. So the cyclist is also in a square refinement region, and which also ends quite soon downstream. Then between the motorbike and the cyclist, there is a relatively coarse mesh. So pretty much all CFD simulations need a refinement region in the wake zone to allow the wake to evolve naturally. Here, there isn't this refinement region. And I think this is even more important for there being a wake refinement region here behind the motorbike than most other simulations out there, because the wake from the motorbike is now impacting the rider, which is what we're actually interested in. As such, I would have thought that a refinement region here would have been better, but perhaps they didn't have the cells to spare. Depending on the distance the rider is downstream, the CFD head up to 77 million cells. And they say that based on their grid convergence analysis, which they say they don't present here for some reason, they didn't need to have this wake refinement zone. But that seems odd to me because pretty much all simulations do need wake refinements, and without the grid convergence info, it's hard to tell what difference this refinement would have made. One thing that is interesting is that they say that they prescribed a turbulence intensity level of 0.5% at the inlet, which is obviously different to the 0.3% they had in the wind tunnel. But the reason why they prescribed such a higher value here in the inlet is that the turbulence intensity decays over time, and by the time it hits the motorbike, it is now 0.3%. And that is something that's really interesting because you really need to keep that in mind when you're doing CFD. And I remember the first time I was doing this and I had a lot of trouble with it. So I wanted to get 0.8% at an airfoil, and I had to run all these different simulation cases to figure out how much turbulence intensity would decay by the time I hit the wing, and hence how much I had to set it at the inlet. So anyway, these researchers did two different CFC setups. They say that for all distances between the cyclist and the motorbike, they did the regular k omega RANS simulation, which means that they are steady state. But for distances greater than 4.8 meters, they then used the URANS k omega SST model. And I'm not entirely sure why they did this. I mean, they say later on that the RANS was more economical but less accurate than the URANS, which is expected. But even still, I'm not sure why they ended up doing all these distances in the RANS anyway. I would have thought that just a few to compare with the URANS would suffice, but maybe they already had done all these RANS ones and found that at greater distances, the CFD started to deviate from experiments. I don't know. Anyway, one thing that is really interesting to note is that the wheels were not touching the ground in the CFD, but just slightly off them. So you can see here, they are off them, and as is the motorbike. They say that other studies have shown that this makes no real difference. The reason why they wanted to have the tire off the ground is because it helps reduce how many cells you need to use, because as the tire touches the ground, you start to get very small areas that you need to fill in. And you can either use large cells with poor quality, like high skewness or aspect ratios, or you can use smaller cells and your cell count will increase. However, given how small the tires are, the increase in the cell count here wouldn't be that much, like maybe 1 million or so. And considering that they already used 77 million cells, this tells me that they were really at the limit of what they could do with their computing resources. I mean, 1% more cells is not a big deal unless you're already pushing things a lot. They also did a time-step independent study, which is good, and unlike the grid convergence study, they do report the results here. But the thing is, they looked at a few time steps and they concluded that a time step of 2 milliseconds, what they're saying here, which gave a current number below 1 in the region between the motorcycle and the cyclist. But if you remember, this region was not refined. So the more I read of this CFD setup, the more I think it is a little dodgy. As I said earlier, even when you don't have an object downstream, you still usually have a wake refinement region. Coupling that with the fact that they do have an object downstream makes me think it's even more important to do so. They also say that they're based on their grid convergence study. They don't give any details on though. They didn't need this wake refinement. But then here now they are saying that their current number was less than 1, but that is because the cells are much larger in this zone than what they should be. And if you were to go around the actual motorbike or cyclist, the current number would be much higher. And I don't know exactly how much smaller these cells are in this region, and hence how much higher the current number would be. But just by looking at these cells, I would imagine maybe around a current number of 5 or even 10 in this region. So that's a little bit suspect. Anyway, another weird thing is that they tested 3 different time steps, 1 millisecond, 2 millisecond, and 5 milliseconds. And for all of them, the drag coefficient was within 0.5% of each other. And given other inaccuracies in their setup, a time step of 5 milliseconds at the expense of a few tenths of a percent of error, doesn't seem to be that big a deal. I mean, they could have just had a bigger time step, made the tires touch the ground, and hence have more cells, but a larger time step would allow them to run the simulation in the same amount of time. Alternatively, perhaps using some of those resources to refine the wake would have been better. As I said, there are some dodgy things going on here, and don't get me wrong, I mean, a CFD setup is quite demanding in terms of computational resources, but if you are going to have this level of CFD setup, then you kind of need to match it in other ways as well, otherwise the CFD isn't that good. Anyway, let's move on with the validation process. So in figure 9, let's scroll down here. We see the drag coefficient reductions for the wind tunnel and the CFD in the top part here. Now, there are a couple things to point out. The first is that the URANS CFD drag reductions line up very nicely with the wind tunnel results, these black lines and orange lines. On the other hand, only when the rider is close to the motorbike, as in less than 2.64 meters, do the RAN CFD drag reductions line up well with the wind tunnel results. As the rider gets farther away, the RAN CFD gets less and less accurate. You can see by this hashed line getting more and more different. So the second thing to point out is that these values are the drag reduction percentages. From what I can tell, nowhere in this paper is a comparison made between the actual drag coefficients between the wind tunnel and the CFD. It's only the drag reduction percentages. That is a problem, because as I've pointed out in other podcasts, when you only see the percentage changes reported and never the actual drag coefficients, this is a very easy way to hide errors in the CFD. Coupling that with the lack of grid convergence data, time-step dodginess, I think the CFD is not nearly as good as what these authors are indicating. So overall, I would rate this CFD to maybe be a 3 out of 10 because there seems to be a lot of massaging of results going on presented here in order to hide things. I could be wrong, but I don't think I am. So from all this, I think we can definitely trust the wind tunnel results, but from the CFD, I think we can only really trust generally their FlowViz data and just a general indication, not exactly what's happening. I don't think we can trust the drag data at all by itself. Fortunately, there is a lot of good data from the wind tunnel experiments. So let's jump to figure 7 and look at some of the CFD general FlowViz to see how the wake is generally impacting the rider. Again, the exact details are not accurate, but the general flow is because the results here are what you'd expect. It makes sense. So when the cyclist is 10 meters downstream, it's quite far downstream, the wake is still quite strong. You can see it's still impacting the rider quite a lot. The velocity is only around 85% of the freestream velocity. And given that the drag is proportional to the square of the velocity, immediately that indicates the drag of the cyclist will be around maybe 25 to 30% lower right there just because it's in a slower moving flow. Figure 8 shows the pressure coefficients, and I would say that at 10 meters downstream, the cyclist is encountering a little bit lower static pressure from the free stream flow. Now, unfortunately, the authors didn't give any more FlowViz data for other distances, which I really wish they had because I'd be interested to see just how much the wake is impacting the cyclist at 50 meters downstream, but that's how it is. And the reason why I would be interested to see at 50 meters downstream is because if you go to figure 9, you can still see even at 50 meters downstream, the cyclist is experiencing about a 5% reduction in the drag. That's amazing because this motorbike is so far ahead and yet the cyclist still can benefit from it. And in fact, this is actually an interesting topic because the more experienced the cyclist is, the better they can feel where the wake is and then navigate into it. So there's been a ton of research about this, and I know quite a few researchers from different research groups and even private companies who have investigated this, and it is remarkable just how well cyclists can feel the wake and navigate into it. So even at 50 meters downstream, I think good cyclists would still be able to feel the wake and still take advantage of it. Now, if the cyclist is a mere 12 centimeters away from the motorbike, the drag drops by 75%. At that rate, it would actually be really easy for the cyclist to hit 100 kilometers per hour behind this motorbike. And even at 2.64 meters behind the motorbike, the cyclist's drag drops by 48%. That's half. That's insane. Now, these researchers did a rough calculation as to how much that drag reduction would benefit a cyclist in terms of time reduction. And in the bottom figure of this figure 9, we see that if the cyclist was only 12 centimeters away from the motorbike, then instead of taking 1 minute to cover a certain distance, it would only take 25 seconds, less than half the time. So over a 5-minute period of riding, very close behind the bike, you'd have a 2.5 minute lead over the rest of the pack. And even at a distance of 10 meters behind the motorbike, you'd only take 55 seconds to cover the same distance in 60 seconds if there wasn't any motorbike, a 10% advantage. So it is clear that the motorbike can pretty much control who wins and who loses. I mean, over a 2-hour race, a 2 or 3 minute advantage is a big deal. And with that, we come to the end of this podcast. I really liked the results from this wind tunnel data. There were some simplifications, but I think the overall conclusions that the motorbike can greatly affect a cyclist's time and the outcome of a race is very valid. As for the CFD, well, I think it was one of the worst ones I've seen, primarily because of what I think is massaging of the data to present it as being much better than what it actually is. And who knows, maybe this CFD will take the prize for worst CFD for this year's podcasts. The moral of the story is, when it comes to any drag or lift data really being reported, it's always good to give the actual figures and not relative changes. If you see relative changes, that's a major red flag. It indicates that they are potentially trying to hide errors, and that might work for inexperienced aerodynamicists reading this paper. But for those who have been around the barbecue a few times, you can sniff it out. And on that note, if you want to learn OpenFOAM, which is a really good free safety software, but hard to learn, check out our link below. We go through from the very basics all the way to very advanced CFD approaches like dynamically morphing meshes. And if you want to do experiments and you have data, did you know that there is probably a 2 to 4% error in your data? In the Atmosphere Hawk link below, we go through the math as to why that is and how to fix it. And with that, we are out for this one. Peace out, amigos.